so that it can handle the worst case signaling scenario in a given circuit. So to start with, we will just use the same example we have been using in this last few slides discussion, like so. So in the given circuit, we will make some assumption. Let's say in the data sheet, it is given that the RP naught is equal to Rn naught. That means the resistance of a unit size PMOS transistor is equal to 2 times the resistance of a unit size NMOS transistor. That's a given information. Now, for worst case sizing, the very first thing we have to identify what input combinations will give us worst case delay for high to low propagation, and what input combination will give us worst case delay for low to high transition. So this is a 4 variable problems, A, B, C, D, right? So when you have a 4 variable binary problem, you can have altogether 16 different combinations of input to the power 4 because it's binary signal. So 16. Out of the 16 combinations of inputs, A, B, C, D, some will give high to low transition, some will give low to high transition. So you have to find for high to low transition the longest series path that will give us a high to low transition, and the longest series path that will give us a low to high transition. So the worst case TPH, low to high, in this particular circuit will be A equal to 1, B, C, D will be 0. In that case, A will be off, right? B, C, D will be on. So there will be 3 transistors in series to make a low to high transition. And for worst case TPHL, high to low, what are the options? I can go through 1 transistor D, I can go through 2 transistor AB, 2 transistor AC, or all 3 transistor ABC on. The worst case, because if you put them parallel, then it becomes a stronger path or weak path. So series of 2 transistor AB or AC will be the worst case scenario for high to low transition. So we selected A equal 1, this is on, B equal 1, C and D will be 0 for high to low transition. First, let us set some target. We want to make sure that our circuit is symmetrical in worst case. That means TPLH and TPHL should be equal. That is the design target given to you. That for this particular circuit, your TPHL and TPLH should be equal. But TPLH, from regular analysis, we know 0.69 are equivalent of low to high, equivalent of P times CL, right? From previous analysis, from TPHL, high to low will be 0.69 are equivalent of N times CL, right? This is given with this general expression for TPLH. Now the question is here, CL is common. If we can find those values, then it will be easy. So now, here, what we want you to do, that from the given condition, I want TP equivalent of NMOS should be equal to Rn naught. So this is a given target. Let's say you want to achieve TP equivalent of N equal to Rn naught, and you want to achieve TP equivalent of P equal to Rp naught divided by 2. That's given target. And if you want to make the circuit symmetrical, that is TPHL should be equal to TPLH to make it symmetrical. Then you have to make sure that 0.69 are not CL, the equivalent, the equal to this, right? We have to, so that's a given condition. Now, for the worst case scenario for TPLH, let's pick one at a time. TPLH is, the general definition is RP equivalent times CL, 0.69. But I want you to meet this target, that RP equivalent should be RP naught divided by 2, right? So RP equivalent is, we know that RP naught divided by W over L of equivalent, because the total equivalent resistance is unit size resistance divided by equivalent size. So we are doing the back calculation. We are trying to calculate the size of that transistor on this series path. Worst case, low to high is 3 transistor on. So now the target, design target for you to achieve RP equivalent of P is RP naught divided by 2. By definition, RP equivalent is this. So now put the target value here, RP naught cancels. So what we have to, for the given target, what we have to achieve? We have to achieve WL size, equivalent size of this 3 series path should be equal to 2, right? From the given target, that's the equivalent size we have to achieve. And that is the equivalent size of what? That is the equivalent size of 3 series transistor. For when we have multiple transistors in series, we don't add their size directly with their, we add their L over W, right? So from the given target, we just calculated that we have to achieve an equivalent size W over L of 2 for this worst case series path. That means L over W we have to achieve is half. So this should be L over W of these 3 series transistor when we are making a low to high worst case transition. Now, the 2 sizing technique algorithm. One is called uniform sizing, the other one is called progressive sizing. So there are 2 transistor sizing algorithm that typically is used. One is called, the one most frequently used is called uniform sizing. So what is the principle of uniform sizing algorithm? In a given series path, every transistor will be of equal size. That makes the design simple. In a given series path, every transistor should be of equal size. And if there are more than one parallel path, then their equivalent sizes should be equal to each other. So uniform sizing is based on 2 principles. Number 1, in a given series path, you have more than one transistor. Every transistor in that series path should be of equal size. Principle number 1. Principle number 2 is, if you have more than one alternative path for signal transition high to low, each parallel path must have same equivalent transistor size, no matter whether you have 1 or 10. So now, for the worst case low to high transition, we have 3 series transistor, and we found out that the equivalent LW ratio would be 1 over 6. And if we apply uniform sizing algorithm, then all 3 of them should be of equal size. That means all 3 of them should have equal L over W. If they have equal, W over L means size, right? So if the sizes are same, so L over W should be same. So L over W of B plus L over W of C plus L over W of D. Together, equivalent should be half. So L over W of P equivalent P is equal to L over WB plus L over WC plus L over WD. And equivalent we just calculated, it is half. If all three of them are of equal size, their LW should be equal. To make this true half, it should be 1 over 6, 1 over 6, 1 over 6. Right? So 3 times 1 over 6 becomes half. So each one of them will be 1 over 6. So size of B, size of C, size of D should be equal to 6. So we assign size 6, 6 and 6 based on uniform sizing principle, algorithm, principle 1. All the transistors in the same series path should be equal to, it should be equal size. Now the principle 2, in each parallel path, the total equivalent size should be equal. So B and C in parallel to A. So the equivalent size of B should be equal to the size of A. Now, B and C are in series. So first we already know the size of B and C, 6 and 6. So, but they are in series. Now let us calculate the equivalent size of B and C. LW equivalent of BC is LW of B plus LW of C because they are in series, right? So 1 over 6 plus 1 over 6, 1 over 3. So each of these two so the equivalent of LW BCQ will be 3. And BC together in parallel to A, they have to have same equivalent size. So size of A should be 3. That's called uniform sizing. So now, in the worst case scenario for low to high transition, I have calculated the size of all 4 transistors in the PMOS path. So this is worst case sizing using uniform transistor sizing algorithm. Now let us look at the high to low transition scenario. Yes.
It feels like my what the calculation is, I get it. It feels like the 6, 6, 6. Okay, I get it. 6 is coming, 6 is coming. When you compare B and C with A becomes 3. So we calculate from the last equation, but 1 by 6. It feels like we're calculating the resistance, right? Resistance, right?
Exactly, you are right. So basically, when you have 2 transistors in series, their resistance adds up. Resistance increases. Resistance is reciprocal to the size.
But the calculation, it feels like it's a capacitor calculation.
It is not a capacitor calculation.
Like
there is no capacitor.
Yeah, I know.
Size.
I know, but what I'm saying, in the capacitor, when we connect in parallel, it becomes half, or I forgot the equation of the capacitor, but feels like
you are confusing with the Elmore relay concept.
Yes.
No, because here in this worst case sizing, we are doing it equivalent inverter model. We are not even considering any internal capacitance. We are just adding the sizes or L over W of the resistance of the transistors based on this
equations.
Equation.
Okay, got it.
So we are not even, other than load capacitance, we are not considering anything.
Okay.
Excuse me.
Yes.
So going up to the WL equals 2, the P equivalent.
Yeah.
Where do we get the 2 from?
That is basically, I can give you a random design target. I want you to design this circuit for symmetry. That means both of them should be, the TPHL and TPLH in the worst case should be equal to each other.
Okay.
That's a design target.
Yep.
And then, and I also told you that, well, they're equal, but what should be the value? The equivalent resistance for P network, PMOS network in the worst case scenario should be equal to RP0 divided by 2. That's the given target. And the equivalent resistance for the worst case and MOS network should be Rn0. That's the design target. I can tell you it should be 4 Rn0 instead of 1 Rn0. I can tell you it should be 2 Rn0 or 5 Rp0, right? So this line is our target is to make the circuit symmetry with this goal. RP, Rn not equivalent, Rn equivalent should be this, RP equivalent should be this. So that is a design target.
So the size, the WL,
So this-
so P equivalent. So
Yeah.
if your almost there equals 2, is that also a given? You give us that as well?
No, this is the general definition of RP equivalent. RP equivalent is RP naught
Okay.
divided by W over
Okay.
L, size of P.
Okay.
Now,
So you found
this one, this is general formula for RP naught and from previous slide.
Gotcha.
For any random PMOS transistor, resistance is RP naught divided by its size. So that is the general definition of RP, the equation we use for. Now, in the given target, I am telling you that you should achieve an RP equivalent of that PMOS network, worst case PMOS network, RP not divided by 2. That's the design target coming from that line. So I am replacing the value of this one here, right? And then, so that's where I got the equivalent size equal to 2. That I should achieve 2 equivalent size in the longest PMOS path to achieve the design target. Yeah. So I can give you another problem. Let's say, let's make TPLH equal to TPLH. It can Rn equivalent is 3 Rn naught, right? RP equivalent is 2 RP naught. I can give you the random design target. You have to basically, if the design problem is given like this, using this general formula, first we have to know what is the equivalent size for the given target for the worst case signal scenario I have to achieve. So bring the back calculation from equivalent size. Now, using the uniform sizing transistor principle, we are distributing the sizes into the number of transistors we have in the series path. And then uniform sizing means that every alternate path should have same delay. That is the symmetry. Equivalent of 2 series transistors of size 6 is equal to equivalent size 3. So that if the signal takes this path or this path, they will have same delay. That's called uniform sizing, that's called symmetry. Now let's look at I want you to do some design calculation again and again. Randomly just draw some circuit and then draw some target and calculate the size. First time it will be a little bit confusing. Go ahead.
So, whatever the circuit we draw, can we do it like RP is equal to 2R NO? So if you use that equation to
Yeah,
solve.
so that's basically, as I said, the first three lines, the first line and the third line here is giving you the design target. And then a second line, I am specifically telling you the worst case input scenario. But your job in actual design problem, in homework and exam, you have to find that worst case. So you will be given
First
the
3 lines.
relative value of RP naught and Rn naught, whether it's 2 times, 3 times, or 1 times. We know that on average Rn naught, RP naught is 2 to 3 times larger than Rn naught.
Yeah.
PMOS resistance versus NMOS resistance. And then our design target will be given to you. Your step 1, for this type of design problem, the number 1 question would be, find the worst case input scenario for low to high transition, find the worst case input scenario for high to low transition. Here I am giving you that answer of the first question. The next is, now select the sizes for each individual transistor using uniform sizing technique.
So the first line and the fourth line will be given.
Yeah, that's your design target.
Second line and the third line we need to find it out by
Yes.
ourselves.
If it is a 4 variable problem, from the 16 combination you have to find which combination. Actually it's not easy. Always look at the longest one. If you can draw the circuit correctly, all you need to know which path will take the longest time to charge it for a low to high transition. I have one path AD, one path BCD. The path that contains the highest number of transistors in series will be the longest path. Yes.
Will the circuit be given, or we need to
You have to draw the circuit. So, actually, one question will be 70% of your take time. One question. Just one question.
Professor, take
Yes.
this. I can't see
Yeah?
the marker.
Okay.
Please,
Okay.
if you don't
So-
mind. I'm sorry.
No, that's fine. So, let's say if I give you a complex logic function, something ABCD, ABC prime D, so on. It's question number one. Minimize it, find the simplest possible, smallest possible Boolean expression using the technique. Question number two, draw the CMOS static version of this circuit. Question number three, draw the P-type dynamic version of this circuit. Question number four, draw the N-type dynamic version of this circuit. Question number five, using the worst case scenario for this design target, calculate the size of the transistor. These are all interrelated. So lecture 3 and 4 and 5 is just building on top of each other. So the first thing you have to practice again and again, how to simplify a logic equation and convert it to NMOS network. If you can draw the NMOS network, PMOS network will be complementary, right? And then if you know how to draw PMOS and NMOS network, then P-type dynamic circuit will have only NMOS network, PMOS network, N-type dynamic circuit will have only NMOS network, yes.
So just so the dynamic is just, it's either the pull up or the pull down network, and then it has a PMOS and
Don't
then
worry
NMOS.
about it, we're going to
Okay,
the
no,
lecture
it's
soon.
I was just like, we haven't covered that at all.
No,
yet, so.
don't worry about it right now. So let's concentrate on the worst case scenario for high to low transition. Okay. So now, here the given target is RPN equivalent of NMOS Rn naught. So first, TPHL we know, by definition TPHL is 0.69 Rn equivalence times Cn. In this given design target question, I am telling you, your N equivalent of the NMOS network in the worst case should be equal to 1 Rn naught. It is given. So, but general definition of Rn equivalent is Rn naught divided by equivalent size. That equivalent resistance is given Rn naught. So, my equivalent size for the worst case NMOS network should be 1. I am giving you a simple number to make it easy for you to follow. So L over W also should be 1. Now, this total L over W equivalent is the result of 2 series transistor AB, right? And we are using uniform sizing technique. That means size of A and size of B in this equivalent series combination should be equal. So LWM equivalent is equal to LWA plus LWB. If the total is 1, each one of them should be half and half. So their size should be 2. Because if LW is half, then W over L is 2. So now, A2, B2, size. Do we need to calculate C? No, because B and C, they are parallel, identical, single transistor path connected between A and the ground. So we should have exact same size coming through here and coming through here. So B and C should be of equal size. We don't have to need calculate. So whatever size we calculate, size B should be set to 2 and 2. Now let us look at D. In any parallel combination, every single path should have equivalent resistance, size. So from output to ground, how many alternative paths we have? 1 through B, 1 through AB, 1 through AC. 3 possible alternative paths. Now, the equivalent size of AB is what? 1, already calculated, right? So equivalent size of AB is 1, so equivalent size of AC also 1, so these should have an equivalent size of
1.
1. So we have the answer for the given target size. Now, this gives you now the complete picture of the whole circuit, sizes of each individual transistor to meet the worst case high to low and worst case low to high propagation delay target. So what is the benefit of using worst case sizing?
We can
It's-
find the in the worst case we can find the actual delay.
Yes. The other thing is that
All
you
those
as the
work.
designer, out of all 16 possible combination, you are designing it for worst case scenario. So for all other 15 combination, you are definitely going to meet your design target. So that's, but commercial design sometime they don't do the worst case sizing because then you are over designing. Statistically, probably 50% of the case you will not face the worst case scenario. Then again you do the best case scenario, 15 out of 16 times you will not meet the design target. So they try to come in the middle, average design. But these are like simplistic technique, actual design principle will be different, yes.
Why is the reason we don't, okay, best case scenario, okay, we don't, I know that there is no accurate we can get it, it's fine, that's why we are going for the worst case scenario.
Yeah.
So what's the problem if we go with the worst case scenario and
Because
design a
that-
problem?
yeah.
I didn't understand that part.
Okay. If you go by worst case scenario, then for every single spot, you have to make your transistor much bigger because we are trying to handle the longest possible delay. So we have to make sure that we have the smallest possible resistance, and to make ensure smallest possible resistance, we have to widen the transistor size. And the real space you have on the chip, semiconductor chip, it's only 2 by 3 centimeters.
And
If you make the transistor bigger, then you cannot put more transistor.
and we have a problem.
Yeah. Go ahead.
But if all of the logical paths are essential for the proper behavior of the circuit, and you end up designing to an average and losing one of those paths, then your entire design is garbage.
No,
So-
it's not. It's not a garbage. You are not getting the expected speed because this logic, this does not affect the logical functionality.
Okay.
If I
Oh.
use size 20 here, this path will be quicker, but the very first thing, come up with the simplest possible accurate logic expression. Once you design it, sizing will affect your performance, sizing will affect your symmetry.
We are doing all this stuff just because we want that the VM that
Okay.
middle path.
Yeah,
of
we want to
the
make,
resistance
first of all,
should be in the center.
Yeah, so two things. One, we want predictable, symmetrical behavior, VM to be at the middle, number one. But actually, even you do all this, they will guarantee that you will be at the middle because signal will be random. But the other thing is that we want to make sure that in the worst case scenario, the transistors, the circuit's performance is not off by 40% from the marketed speed. But practically, can we ever get the prescribed speed in cell phone, in laptop or anywhere? No. That is under optimum ideal lab condition that 3 gigahertz frequency we can get, right? So that's why we'll always fail by a certain percentage to meet the specification mentioned in the commercial packaging. But we want to minimize that discrepancy as much as possible by doing this type of technique. Yes.
I have 2 questions.
Yes, go ahead.
So the calculation what we have done. Now I remember the it's called the resistance calculation. When you say 20, that makes more sense that in C point, in C, if we put 20, the resistance will be small and it will be very fast.
Yeah. So basically now if I make this size 20, so let's say this is size 2. Size 2 means 20 nanometers technology.
Yes.
We are utilizing 40 nanometer of chip space. Size is technology, right? Size 2 means 2 times the technology. If you are using 10 nanometer technology, size 2 means 2 times 10 nanometer. So you are taking 20 nanometer for each transistor. If you make size 20, then you will be taking 40 nanometer, but I want to put another 10 transistor for other logic circuit in the cache. So the problem is, yes, you want now, as you are making it wider, resistance is becoming smaller, but the parasitic capacitance is increasing because that is parallel proportional to the area.
Okay.
So that the power consumption will go up, signal delay will increase because it will increase the reducing the resistance, right? But it is increasing the capacitance. Why? Because tau is something RC. So that's why you cannot just unilaterally say that I will make the transistor so large that it will have a very small resistance. Then this capacitance will be so large that you lose the benefit of decreasing the resistance. So it's an optimum design.
And also, when you calculate the resistance of this section B, A, B, and D, the power consumption is also the same.
Same. So that's the symmetry. We want to make sure that every single part sees same amount of, reasonably close to same amount of parasitics, resistance, capacitance combined, so that they suffer similar delay, similar energy consumption. Of course, there will be many other factors will come because we are ignoring the internal load capacitance here. So if we consider that, that will be much more complex analysis. But just to give you an idea how sizes are selected in a design. But in a complex design with billion transistor design, there will be probably some automatic algorithm in Intel company or AMD or NVIDIA. They have the proprietary algorithm to select those size, like block by block, right? Yes.
I have a last question.
Go ahead.
So we remember that formula of series circuit and parallel circuit.
Yes.
We are doing the reverse way to calculate the the D path is 1 and A and B is 2. So when we combine this with the D, the consumption is the same, right?
Yes. So because you have to just visualize the relation between size and resistance. Wider the size, if they are in parallel, you are adding the sizes. Resistance are going down. If you are adding them in series, you are adding the resistance. Resistance is going up. So, but since resistance and size, that relation is reciprocal. W over L and resistance. Resistance is inversely proportional to W over L. Then when resistance is linearly proportional to L over W. If you can visualize that relation while writing this, then you will not have any confusion.
That's what I was thinking.
So I want you to draw some random function and actually do the problem by yourself. Okay.
Can I have
Yeah, go
the
ahead.
last
Yes.
request?
Yeah.
Can you give us some assignment regarding this kind of formula?
Okay, actually there will be.
You told us if you give a formula, it will have 16 steps to reduce into 1. Can we have that kind of formula so that we can?
No, I've not. It depends on what function.
Function, yes.
It doesn't mean 16 steps. It depends on how good you are in Boolean algebra.
That's what I
Yeah.
want to practice.
Yeah, so yeah, you can write any random, if you want, I can give you some targets.
Yes.
Okay, go ahead. Any question from here? Okay. So, we just described the worst case uniform sizing. Now this one is, they call progressive sizing. So progressive sizing actually captures the real scenario. In terms of design efficiency, performance target, it is much better, but it is very, very time consuming and complex. So the transistor sizing, as I mentioned, there are two possible algorithms or technique, uniform sizing and progressive sizing. Progressive sizing takes into account the circuit structure we explained in Elmore delay. So let us go back to this Elmore delay structure. This is my ground or VDD. I am charging or discharging the series path of 4 transistor or 5 transistor from here, right? So this resistance, what is this? It is the transistor's resistance close to the ground or close to the supply. If it is an MOSFET, it is close to the ground. So this transistor is handling discharging current for all 4 of them. This transistor is handling discharging current or charging current for 3 capacitance. This one for 2. This one is only handling for 1. So like a regular water distribution network. From River, Missouri, where they are drawing the water from Greater Kansas City area. Let's say it is coming from east, crossing through Independence. The pipeline, the width of that pipeline from the River, Missouri to Independence must be wider. Then it is crossing to Raymond. Then it is coming to Kansas City. Then it goes to Overland Park and further, right? If it goes in the westward direction from east from the Missouri, initially close to the river source, the pipeline has to be bigger, wider. Successfully by the time, let's say it ends in Topeka. That should be the narrowest, right? So whichever path handles highest amount of charge, or whichever transistor, in case of pipeline, whichever transistor handles highest number of charging and discharging capacitance, that should be the widest, and the one handling the least amount of charging and discharging should be the tiniest in size. That is called progressive sizing. In that way, so uniform sizing, what we are doing? Uniform sizing, we are making entire pipeline width from River, Missouri to Topeka, same width, without considering the fact that end of the road, you don't need that much wider pipeline, right? So that is very common sense design technique. That is called progressive design. Now let's say, look at this, a random logic circuit. It has n number of transistors in series from output to the ground. For making a high to low transition, let's say every node has an internal capacitance. Every node will have an internal capacitance in real circuit. So as I am charging or discharging, this transistor M1 will be handling discharging current for everything upward. This one will be handling 1 less. This one will be handling 2 less. This one will be handling only charging or discharging for this one single transistor. So logically, this one close to the source should be the largest in size, the widest in size, and this one should be the smallest. So the size of M1 should be greater than M2, that should be greater than M3, so on. That's called progressive sizing. For complex design technique, by using, for complex logic gate, by using progressive sizing, we do not need to make them all equal worst case scenario, because this one will be handling the highest amount of charge in the worst case scenario of the entire series path when it's on. So that saves lots of chip resources, and that speeds up the circuit, because if I make them smaller, its parasitic capacitance and everything, all those will be less and less. It will take less area. If it has less parasitic, it will consume less power. So it will speed up the circuit, it will save area. So that's called progressive sizing as opposed to uniform sizing. But for complex logic gate, if you are talking about a billion transistor, then you cannot go and test each and every logic circuit. So what they do kind of a combination of uniform and progressive sizing. So the actual IC companies, they will have algorithm. Okay. For this block, they will, let's say you have 6 transistors in a series, they will divide them into 2 blocks. For block 1, select one size. Block 2, closer to ground, select slightly larger size. So they do by a combination of progressive and uniform sizing. Within the smaller block, it's uniform, but in block by block, it is progressive. So some sort of combination of these 2 techniques that are used in the actual algorithm, design algorithm they use in real commercial IC design. This is now your decision to use uniform sizing or progressive sizing does not affect the logical functionality of the circuit. It will only affect the performance. So that's why it is a design technique to improve the performance, but it has nothing to do with the functional correctness of the circuit you are building. You will still get the same function later or sooner with less power or more power, but this is a kind of intuitive design technique. So one of the biggest problems in CMOS circuit is the presence of series transistor. Every time you have one more series transistor added, look at this, the terms getting bigger and bigger. Right? One more internal capacitance and you are getting like much bigger term. So another design technique for complex logic gate that is frequently used is to divide the logic gate into smaller logic gate. How does it? It's called. So let's say you are given the task to design a 4-input AND gate, right? Actually, you get an AND gate followed by an inverter, right? This is what it is. Now, this is a 4-input. So, in the NMOS network, you will have 1, 2, 3, 4 transistors in series, right? But logically, I can implement this like can I do that? Because two input AND gate followed by a NOR gate also give me a F equal, let's say, AB plus C, ABCD. So here I am getting ABCD, here I will be getting ABCD. But if I do this also I am getting ABCD here. Same logic. So I am dividing a complex logic gate into smaller logic gate. So each one of them now will have maximum 2 transistors in series here, and this one will have 2 transistors in series. This one will have 2 transistors in series. So 3 individual series paths. So the transition will be quicker. So that is the
Did you need to draw an XOR?
yeah, XNOR. Yeah.
Okay.
Because I can draw AND gate, right, with a OR, right, and then I have to put an inverter here to make it. So this one, we have to basically, because here I'm dividing them into, I have to double check, but this is maybe not, but I'm giving you that's the idea. So this is basically what I have, right? 2 NAND gates followed by an OR. Here I am getting A, B, C, D, bar. right? Now if I put an inverter here, then I get here A, B, C, D. And OR followed by, no, an inverter is nothing but a no, right?
Right.
So actually this should be the case. Okay, so that's when we have, this is basically one example, design technique. 3 I'm talking about, I see it 2, I will explain later. So you have an 8 input, you have an 8 input AND gate to be implemented, 8 input NAND followed by an inverter. I can divide them into 2 4 input NAND gate followed by a NOR gate. And each one of them can be implemented by this, right? So now, you as a designer, you have option to implement it directly. So the longest series path will contain 8 transistors in series, or you can choose this option. Longest series path will have 4 transistors, or if you can apply this implementation logically, same thing, each series path will have 2 transistors. But here another thing you are reducing the vertical length, but you are adding horizontally more step here. Here you have 1 or 2 logical step, 1 2. Here you have 1 2 logical step, right? So this one is comparable to this one, but here you are reducing the vertical length, but you are adding 1 2 3 4 horizontal logical step. So this one will reduce the series path vertically, but it will increase the length horizontally. So typical standard practice is to keep it maximum 4. So from performance point of view, this one will be better than all 3. So we will start from here. If needed, we will revisit last 4 5 slides again, because the sizing, it will take some practice.